Hi guys, I'm Max, and today you'll be joining me where I run through my skin cancer classification project. So yeah, I'm going to put up some slides, run you through the project, and we'll do a little bit of a demonstration. If you have any questions, just pop them in the chat. I'll try and answer them as I go through, but if not, there'll be some time for questions at the end too. So yeah, let's get started. So a little bit about me and the project. So I'm a mechanical engineering graduate. This is where I sort of first learned about machine learning. My final year master's project was all to do with images. So that's sort of where I picked up the basic techniques I used in this project. I then joined Rockborne last year in January 2023, gained some more formal training around data. So yeah, this project was inspired by a Kaggle competition on skin lesion classification, but I wanted to sort of take it a step further. And as opposed to just running machine learning models locally, make them into a web app that's more accessible and that people can use more easily. So yeah, what am I going to go through today? We'll have a quick introduction, so a bit more in depth around the project, then the data set I found, so the one from Kaggle, a bit of the EDA, so that's the exploratory data analysis that I did to have a first look at the stuff, data pre-processing, so how I got everything to be in the right shape for my machine learning models. Then we'll actually go through the models. I'll do a bit of a brief intro into how the techniques work. We'll then go through my web app, a little demonstration there. I'll go through the conclusions, what I've learned and what I'd plan to do in the future. And then, yeah, as I said, open it up for any questions. So, introduction. First things first, skin cancer classification. What is skin cancer? I'm sure lots of you have heard of it. It's one of the most common cancer types globally. Obviously not a very nice thing, and as with many of these things, the earlier we can detect it, the better for the outcomes. So yeah, as it says here, if it's detected at stage 1 as opposed to stage 2, we go from almost 100% 10-year survival rate to 65% survival rate. So the quicker we can detect this, the better. And yeah, dermatologists and doctors rely on visual inspections for diagnoses. So we can bring in machine learning to classify this as an image classification problem. So I've mentioned it's an image classification problem. What does this actually mean? So it's a machine learning technique that we use to categorize images. So you may have seen ones where you can upload a picture of a cat and the computer will tell you that it's a cat. It's the same thing here, but a slightly trickier setup. So we're using neural networks, and this would allow us to potentially classify the skin lesions faster and hopefully more accurately, and this will relieve a lot of strain on resources, so you don't have to go and see a doctor, so it takes less time. They then also have more time to do other things. So yeah, I've mentioned that this is not as easy as just classifying cats and dogs. Take this example. These two images to the human eye look fairly similar. They're a brownish patch of skin. But yeah, the difference between these, the one on the left is a benign mole, so just your everyday mole, and the one on your right is melanoma, which is a form of skin cancer. Obviously, there's a big difference between these two, and it'd be quite hard to pick it up just by eye. Okay, so now for my project, for my app, what have I used? So I built it all within Python, and for the machine learning side of things, I've used TensorFlow, just the orange logo on the left, which is developed by Google. So that's where all the machine learning happens. And to wrap it in the web app to make it more accessible, I've used a framework called Flask. So the data set I found, the MNIST HAM, Human Against Machine 10,000. Confusingly, this has 10,015 images in the data set, but this is all publicly available and non-identifiable. I've added a little link there if anyone wants to go and check it out. But the key thing to know is that it's all labeled in 7 categories. So they're all there, the 2 in bold, so the basal cell carcinoma and the melanoma are the 2 cancerous ones. The rest are benign. Number 6, melanocytic nevi, which is your mole, is another very common one. Also, it contains the patient's age, the gender, and the localization of the lesion, so where on the body it was. So yeah, now that I've found my data set, I had to go have a look through to make sure I understood what I was working with and what techniques might and might not work. So the first thing I looked at was how much of each of these lesion types do I have? And as we can see here, in blue, melanocytic nevi, so your moles, are very common. That's 2/3 of the data set. So this straight away identifies it as a sort of imbalanced problem. We have about 16% between the orange and the red category. That's melanoma and basal cell carcinoma that are of the cancerous classes. The next thing I looked at was, I mentioned that we had some extra information about age and things like that. So I had a quick look at the distribution of ages. This was just a quick histogram. We can see a slight left skew, so that means that the average age is slightly to the right, which you'd sort of expect an older population. With these things, it takes some time for them to develop on you. So the older you are, the more likely you are to have some kind of skin lesion. So now, does your age affect which kind of lesion you have? Now, looking at this overall, it's quite hard to see because it's so dominated by moles, which is that orange class in the middle. Now, these appear to be fairly normally distributed with age, so it's sort of however old you are, you're equally likely to have a mole. The other classes seem to be where the left skew is coming from. So to sort of be able to see this more clearly, I brought it down just to between moles and basal cell carcinomas and done this as a density, so it takes out that impact of there being so many more moles. Here, yeah, again, we can see that the moles are more prevalent in the younger people and the basal cell carcinoma are more prevalent in the older people. So this sort of told me, okay, maybe if I can bring age into the model as well, there might be more that the machine can learn from. I had a look at localization. There were 15 different localizations in the data set. The majority of them were in the back, lower extremity, and trunk. This is sort of to be expected. Those are bigger areas of the body. Your chest, your back is a big area, so you're more likely to have a skin lesion there. Yeah, that's what I've said there. Okay, so now I've had a look through the data set. I have an idea of what I'm working with, and I'm having some ideas. Okay, there's an imbalance. I need to address that, and maybe the age and things will come into play. So now, data pre-processing. So going from that to let's get this ready for the models. First things first, checking, do I have any empty values? So the only column that had any values missing is the age column. I had 0.5% of the values there were null. So I just replaced these with the mean, and then the model will see those as not having an effect, essentially. Just to sort of speed up the training process, because images are large file types, I've resized these, I've shrunk them down to be 100 by 75 pixels. This is not having, well, it's removing some information to make the training process much faster. Then for the machine learning as well, I need to split the data set into 3 sections. So I have the training data set. This is where the model learns all of the patterns that are in the data set. I have a validation data set, and this is what I use to say when I should stop training, when it started to overfit to the underlying data set. And then I have a separate testing data set that I can use to see how well that training has happened. Also, because I've sort of set this up as a project where I wanted to make it more accessible, in the data set itself, the images are fairly consistent. They're all, a similar level of zoom, similar lighting. But if I were to make this available to other people, the images they upload are not necessarily going to be like that. So I want the machine learning to be able to see a wider spread of things. So I can apply some zoom, some translations, some rotations to each of the images to sort of randomize them a little and give it a clearer, more well-rounded view. Yeah, I should highlight at this point as well, there was a big limitation of the data set, and that was on diversity. Almost all of the images were on lighter skin tones, and this will likely bias my models towards these. So yeah, for darker skin tones, the models I've trained probably won't perform very well, and I take the accuracies I have later on as being for lighter skin tones. Okay, so now I've got my data set, I understand it, I have it ready for my machine learning. How is the machine learning actually happening? Okay, so for image classification, I've used convolutional neural networks. What do these mean? Okay, so they're neural networks and they use convolution layers. This is the sort of general overview of the structure. You usually go from some input have some convolution and some pooling. This may well be repeated, and this section is known as feature extraction. This is where we're pulling out the general patterns in the images, and this will get deeper and deeper and more finely looking in more fine detail at the image. This is then connected to a fully connected or dense network where the classification occurs, and the output layer will just be the probability of each of the classes. Okay, there's a lot to digest there, so we'll break it down. The convolution layers. So this is where we have a filter. So this is the 3 by 3 array in the middle here, the 0, 2, 1, 4, 0, 1. And we're putting this, essentially stamping it on top of the input image, moving through the image and seeing how similar the input image is to the filter. So you may have some filters that are checking for edges, checking for circles, all of these things, and you will then receive an output array of how well that filter matched with the image at that location. So this is just giving you a map of where there are edges, where there are corners, things like this. And then you build up a whole load of these maps, and by putting them together, the computer can extract patterns from the underlying image. But yeah, these maps are quite complicated. There's a lot left for the computer to digest, so we use these pooling layers. This is condensing the information down so that it can identify the most important patterns. Typically, we use max pooling, which is on the left, which is where it pulls out the maximum value from the pooling size. So this is where we have the best matches with the filter, or you have average pooling, where you pull out the average of the pool. So this would be sort of smoothing out where there were better and worse matches. Okay, hopefully you now have a better idea of at least the feature extraction side. I won't go too much into the classification side, just sort of think of that as a black box where it brings in all these features and it works out what it will probably be. So now that we've done that in general, how have I applied that in Python? What's the implementation look like? So first, on the top left there, we have the data augmentation section. This is what I spoke about earlier, with randomly flipping, rotating, and zooming the images just to make them more generalized for the real-world application. Then for some of the models, there's some extra pre-processing. So this is for one of the models that I've brought in externally. MobileNet, they have their own pre-processing function. So I just pull that in. I pull in their base model, just apply that very simply. And then here we have some of the pooling that I talked about. And then a final prediction layer. N classes there is just the number of classes we have in the data set. For us, that's 7. And then you can very simply just put that together as a TensorFlow model. So this tf.keras, that's TensorFlow. Select an optimizer and compile the model. Okay, so what kind of models did I build? Well, I started out simple. I combined 7 classes down into 2, cancerous versus non-cancerous, just to sort of get an idea of whether or not this is feasible. I then built that up into a normal convolutional neural network with all 7 different classes. The next 2, VGG16 and MobileNet, are models that are already available as image classifiers, but they're general image classifiers. So I use a technique called transfer learning, where we just take that classification section at the end of the model and just train that on a new data set. So I keep all the feature extraction they've already learned from general image classification, and then just change the classification part to be specific to this problem. And then, yeah, as I mentioned, I'd noticed that things like age, sex, and localization of the lesion could have an impact on the probability of what lesion it was. So I built my own model that combined the convolution side and a dense side about the multi-input model. Oh, I'm seeing a couple of questions coming through. Replacing age with the mean. I think the age distribution with mean and median would be better, right? That's a fair point. You could use median as well. I've seen in general people use the mean. I don't think it would have had a massive impact in this just because there's so few that are gone. I'm assuming you have to specify where the lesion was located when you have to shrink the image, only focus on the areas where the lesion was present, right? Joseph, I'm not sure I quite understand your question. The lesion location is specified separately. So there'd be an image, it would say which class it was, where it was, the age of the patient, and the gender of the patient. Once I've shrunk the image, it's not changed where the lesion was, so I just leave that value as was. Yeah, sorry, I've just seen those two questions. Okay, so let's run through these models and their performance. So starting it out simple with the binary classifier. So on the left here, we can see a confusion matrix. So as we read across the top left, these are where the image was of a non-cancerous cell. And when it was, mine predicted 76% of the time that it was non-cancerous, and 24% of the time it was incorrect and predicted it as being cancerous. Now, when the image was cancerous, only 4% of the time did my model get it wrong, and 96% of the time it identified it correctly. So this is sort of what I'd been optimizing for as I was training, minimizing these false negatives in the bottom left of the grid. So correct values go along the leading diagonal, so the 76 and the 96. But with things like healthcare, it's more important to not give someone a negative when they have a positive. So if someone has cancer and I tell them they don't, that is worse than if they don't have cancer and I tell them that they do, because then they'd just go and get it checked and there'd be no harm done. Whereas if someone had cancer and I tell them they don't, then they won't know. So yeah, that's a real big one to try and minimize. So yeah, I had good performance here, so I thought I'd try and expand it out to the more general model. So yeah, now this grid on the left is the same basic principle, but now split across 7 classes. So again, this leading diagonal, if you go 18%, 52%, 51%, so on and so forth, those are all the ones that it's classifying correctly. As we can see here, there's a massive spike at melanocytic nevi. This is because for this model, I hadn't put any balancing in. So basically it's saying, oh, loads of the images I'm getting in are melanocytic nevi. If I say almost everything's melanocytic nevi, I will get lots of it right and give myself a big reward. Obviously, that's not the behavior we want to train it into. So later on in some of the other models, I've addressed this issue. So VGG16, so this is the first of the ones where I use transfer learning. As we can see, I've still not put any balancing in here. So again, there's a massive spike at melanocytic nevi. But overall, better performance. This has much more layers, so you can pull out more detailed features. Moving on, mobile net. So here I've started to add some balancing. So you see a massive drop in the classification percentage on melanocytic nevi. But in general, as we go across the leading diagonal, it has in general increased. And now for each of them, the one on the leading diagonal is the top or joint top classification. So most of the time when it gets that image, it's classifying it correctly. Obviously, for some of them being as low as 35%, this is still not a very good percentage, but it's a step in the right direction. So now we have my multi-input model. So we can see on the left-hand side, all of the convolution layers. On the right-hand side, we have a separate input, which is the age and the localization and things like that. And we can see this balances it even more. So now we're getting, yeah, everything with almost 50% of the time it being correctly identified. So this is much more promising. Potentially there'd be some way to combine the sort of performance of mobile net on the left-hand side and then having the input layer as well. This is sort of things we'll be talking about when I look at my future work. Okay, so these models are all well and good, and the confusion matrices give us a decent idea around how accurate they are. But that's on, as I said, this pretty consistent data set that I've found online. When I go out and give it to other people, how do we know that it's still performing at that same level of accuracy? So the technique I've chosen to go with here is GradCam. And this sort of looks at which areas of the model are firing when it's given a particular input image. So why is this useful? Well, firstly, for me, I can just sort of see issues and biases. So if it's always focusing on a particular section of images, that can be interesting. Can we use GAN for addressing the class imbalance? Potentially. So for those that don't know, a GAN, a generative adversarial network, has a generator, so that would generate the images, and it then compares those to normal images and sort of learns from the difference between my generated and the accurate. You could potentially use that to address the class imbalance. I'm not too familiar. I've not done too much with GANs. I'd give it a go and see what happens. That's the way I usually work with machine learning. Have a Google around, give it a go yourself, and that's the way you'll really learn. So yeah, moving back to GradCam. So can help us identify potential issues and biases. And then once I upload other images, we can see if it's really focusing on the right areas. Maybe it's easiest to see this by looking at an example. So if I input the image on the left, and then we look at the activation map, you can see that the higher levels of activation, so the yellows and the greens, are focused around where the lesion is in the image. So the model has accurately identified where the lesion is and is making its prediction based on that lesion, not based on just some random pixels in the corner. If it were to have been basing them on some random pixels in the corner, we might say, okay, it's not generalized well to this image, perhaps don't trust the results you get. So yeah, this is sort of in there as a little safety check for people who would potentially come and use my models. So yeah, we've now built the models, we've built a little validation thing. Now time to do what I said I'd set out to do and make it more accessible. So this is building the Flask web app and makes it much easier rather than having to run my Python script, upload files in there in the correct way. I've just created a Flask app in Python. So it means people can go through, see all the EDA I've shown you here and some more with explanations of the models, the training, their performance, what I found in the data set. And then based on everything they've seen, they can select one of the models and upload an image, and then they'll receive a classification. So I'll now jump into a quick demonstration. Hopefully this works. Yeah, so currently all the code for this is not being hosted anywhere. So I'm just running this locally. All the code is available on my GitHub if you would like to bring it into your local environment and run it there. So the homepage just sort of runs through the data set and each of the types of skin lesions. Each of these more infos takes you out to a sort of official medical advice on each of the classifications. If we then go to EDA, so these are these same graphs we showed earlier. This is showing localization with all of the 15 different classes here, and there's explanations to the side as to what's going on and what's happening. Then we have the lesion type by age, cell type distribution. There are a few other ones. So then I showed the combined of is cancerous versus non-cancerous, which is what was used for the binary classification at the start. Then comparing by sex, if there's any difference between the female, male, and unknown. So yeah, there's more information there that you can read through as and when you please. We then have the model comparison. So these are the same classification matrices and the structures here. So it has a quick overview of the structure and how it performed. These are each of the same 5 models that I had before. Yeah, all the same stuff. So now we can go to image upload. You just quickly press click file, upload the image you want, select which model you want. We'll go with just the binary model for now. Press upload. You can quickly see the image just to double check that. Open results in a new tab. And very quickly, you will get a classification back. So it gives you a quick breakdown of what classes it thought it was, and then a confidence. Just to save time, I've run this beforehand with the multi-input model. And here the image was of a melanoma, but it was from the data set. So it should perform well on this. And yeah, with 85% certainty, it says that it is a melanoma. I think there's a slight chance it could be a benign keratosis-like lesion, and then very tiny chance of it being a regular mole. And then, yeah, here, as I said before, we have the GradCam. So we can see that it's really focused in on this central part of the mole here. So this is a good indication that it's seen what we were looking for and someone can trust the classification that was given. Okay, any questions on that? Didn't the compression of the images result in a loss of information from the images? Yes, Sanskar, it did. This is, yeah, again, I'll sort of cover this in future work. Retraining the models with higher resolution images would potentially lead to better results, because if there's more information, there's more it can learn from. So it was sort of a sacrifice made because of the time scale provided to do the project. I was more so focused on trying out new techniques, trying different methods than purely optimizing for performance. So yeah, there's work to be done on making them better. That is definitely true. If I hop back to my slides, here we are. We're almost there now, and then I'll open up for questions. So yeah, conclusions. What did I learn as I went through? So the data set had a good explore of the human against machine 10,000 skin lesion data set. Tried out some EDA techniques I've seen, looking into all the potential things that could be useful for my models. So yeah, talking about EDA, there was imbalances, potential bias with the diversity. So yeah, it wasn't the perfect data set, but it was good enough to get this sort of proof of concept up and running and see what is happening. Another question from Jorge or George, I'm not sure. What is the margin of error when compared to the images of the total result or model? Again, I'm not entirely sure what you mean by what the margin of error is compared to the models. I'll leave that for now. If you could rephrase that, I'd appreciate it. If not, I might have to just leave that, or message me on LinkedIn afterwards, and maybe we can have a more in-depth discussion. Evaluation. So I built several models, used some different techniques, transfer learning, multi-input models, binary classification to get started, and compared and contrasted the advantages of each of these. I then wrapped it in a Flask app to make it more usable and more accessible. So future work. Weighting and balancing. So we saw that in some of the earlier models, I hadn't balanced out the data set, so it was just learning to predict melanocytic nevi a lot of the time. So first things first, apply that to each of the models so that they're all balanced and have a fairer chance of performing well. Yeah, as people have highlighted, fine tuning. So there's so many parameters in these models that can all be optimized. Training with the full-sized images. There's lots of things that can be done to improve the model performance. But yeah, as I've sort of said, my priority was to try out different new things and make it into this more accessible format. There are some slight issues with the GradCam report generation. There's some inconsistencies with, sometimes you'll run it with the same model and it will somehow produce a different GradCam image. So that needs checking and working out. Yeah, GradCam doesn't come with TensorFlow as is. So I sort of had to take the code from Torch where it is available and try and reproduce that myself. I think there might be some issues. So if anyone wants to look through my code and see if they can spot them, you're more than welcome. Be my guest. And then, yeah, once all these models are up to scratch and performing well, I'd like to launch the app to at least be able to be publicly seen. If not, well, I don't think it's anywhere near being used as a medical tool yet, but it would be nice to see people interact with it and get feedback that way. Yeah, so here's some of the references from things that I've used throughout the PowerPoint. Be sure to check those out. And yeah, now some more time for any questions you may have. So just pop those in the chat and I'll answer them to the best of my ability. And yeah, if anyone wants to see any of the code, it's all available on my GitHub, maxcollins457. Can I post a link in the chat? I'll post a link after if people would like. And there's also a blog that should be available if you want to have another read through as well. But yeah, keep those questions rolling in, people, and I'll see what I can do to answer them. Hope you enjoyed the talk. It's been a pleasure.